we have drawn up the diagram for proposition 12. I'm just going to go through it quickly. So we have the conic surface. Through it, we've drawn an axial triangle, ABC. Then we have another section, DFE. We've drawn it so that DE cuts BC at right angles. Then from A, we drop AK so that the diameter FG is parallel to AK. Then we pick some random point on the surface of the section, and we drop it to FG such that MN is parallel to DG. Then we create the parameter or the kickstand or the upright side, whichever you want to call it, FL. We create FL so that it is in this relationship to these things. We constructed the section DFE so that it would hit the upper conic section at some point H. We draw a line HX so that H intersects with L and then continues until it meets NX, and NX is a line extended from N, which is parallel to FL. Then at L, we drop LO, parallel to FN. We drop XP, parallel, connect PL. Same thing to create this little part of the rectangle. I think the only thing I forgot to mention is that FL was constructed at right angles to the diameter FG. And then as we start the proposition, we're going to construct a line through N, R, and S. And R and S is going to be constructed parallel to the line BC. Okay, I think that's all of it. So the thing we're going to start with first is R, M, and S. R and S, as I just said, was constructed parallel to BC, and MN was constructed parallel to DG. So that makes R, M, and S all in a plane that's parallel to the plane of the base, BDC. So if they're in a plane parallel to the base, that means that they would cut off a circle. In a circle, if you have a diameter, and then if you have something drawn at right angles to the diameter, the rectangle made up of the parts of the diameter is equal to the square on the part cutting it off. So MN is the thing cutting it off. The square on that will be equal to the rectangle RN and S. And I've put up our given here. And if we look at this side of it, KA to BK, KC, I'm just going to write that out. And since these are both figures, they represent multiplication. So we're going to write out what they would be sort of unmultiplied, uncompounded. And that would be one line here, KC, with one line here, BK, compounded with KA, KC. If you want to know what compounded ratios are, I talked about that briefly in my previous video on Proposition 11. And so, since these terms are the same as these terms, we're going to substitute. We're going to do FHFL. Is KABK compounded with Ka, Kc. Okay, so now we're going to take a look at these two parts of this ratio, and we're going to try to eventually substitute them out. So let's take Ka, Bk. That would be Ka, Bk. So these two lines exist in this triangle, BAK, and a similar triangle to this, just visually you can see, would be BGF, because FG and AK were constructed parallel to one another. So KABK as Ka is to Bk, GF is to BG. And within this triangle, FBG, we see this smaller one, FRN. And since RNS was constructed parallel to BGC, that means that they're similar triangles. So as GF is to BG, FN is to RN. So we'll stop that one there. So we found terms that we could substitute with these. Now let's look at these two. So let's copy Ka, Kc, and let's see Ka, Kc. Well, this is also similar to the triangle HGC because AK was constructed parallel to HG. So as Ka is to Kc, Hg is to Gc. And in this larger triangle HGC, this part NS is cut off parallel because RNS was constructed parallel to BGC. So HNS is similar to HGC. So as HG is to GC, HN is to NS. Okay, so now let's substitute. You've got KABK, KABK. We've got KAKC, KAKC. So let's substitute KABK. Well, hold on. First, let's bring down FHFL. Let's substitute KABK for FNRN. And let's substitute KAKC for HNNS. Alright, so now instead of having this in the compounded format, let's put it into the format of the figures. So let's bring this down, FHFL. And then this would be Fn times Hn, which would be the rectangle, Fn Hn, and then Rn times Ns would be the rectangle, Rn Ns. And again, if you want to see more about compounded ratios and figures, I went over that briefly in the last video. So now we're going to just construct a ratio between Hn and Nx. And we're going to multiply both of these by the same line, and in this case the line is going to be Fn. So as Hn is to Nx, Hn times Fn is to nx times Fn. And if you look at FH and FL, they're a smaller triangle with this larger triangle, HXN. So as FH is to FL, HN is to NX. Okay, so now we're going to substitute. So on this side we've got FHFL is this string of things. We've got as HN is to NX, this string of things. And we've got as FH is to FL, HN is to NX. So that means that if these two things are at a ratio, these two things are also in a ratio. So let's substitute. So on this side we've got FNHN, RNNS, then we've got FNHN, NXFN, Alright, so on this side over here we've got the term FNHN, and on this side over here we've got the term FNHN. So if things have the same ratio to the same thing, then they're equal. And one of the first things that we had up above was Mn is equal to the rectangle RNNS. So the square on Mn equals the rectangle NX Fn. And that's what it was required to prove. Just looking back on the diagram, that makes the square on the ordinate here equal to the rectangle made out of our kickstand, plus some constant amount. See, for the parabola, the result was that the square on Mn was equal to the rectangle FNFL. But for a hyperbola, we add this rectangle LPXO. You'll see in the ellipse proof, which is the next one, that we'll have to subtract an amount. So yeah, but for now, that's QED.